so first of all, let's draw the Lewis structure for oxygen. All right, oxygen, elemental diatomic oxygen. All right, the first thing that I recommend people do is figure out the S equals N minus A rule first. That's going to tell you the total number of shared electrons in your atom, which is going to tell you the total number of total number of shared electrons in your molecule, which is going to tell you the total number of bonds in your molecule. So first of all, the easiest thing to figure out is the actual number of available electrons. Okay, and let me just stop for a minute and tell you something about these Lewis structures. This Lewis structure business is like a puzzle. This physically is not how molecules are really put together, I mean, as they're forming from individual atoms. But what this is a tool that chemists use to help them predict the types and number of bonding and non-bonding pairs of electrons that they would find in a given molecule. And they're called Lewis structures because the person who came up with them was somebody named Gian Lewis from, he was a professor in California, I think it was Caltech, like 50 or 60 years ago. He was teaching general chemistry to college students, and he was trying to figure out a way to make it easier for them to be able to predict structures, you know, how atoms are put together, and then ultimately what we're going to get to down the road is like shapes of molecules. And so this was his tool. So this is a tool. And so what you do is you just assume, like to figure out the number of available electrons, is you say, okay, in this molecule I have I have oxygen, and I have two of them. I have two oxygen atoms in this molecule. And oxygen is in, let me see, if you need to have a periodic table handy to do this. Oxygen is in group 6. Here's an old periodic table. I'll just throw this up here. Oxygen is in group 6, so that means it has 6 valence electrons. So since bonding is all about shuffling electrons around in the valence shell, then I know that oxygen has 6. So the available electrons here, I have 2 oxygens. Each oxygen has 6. So that's 2 times 6. That's 12 electrons available to work with to pull together this molecule. All right, and so needed, the N, how many electrons, if you had to satisfy the octet individually for each atom, oxygen, you have 2 of them, and if the oxygen was all by itself, to satisfy its octet, it would need a total of 8 electrons, okay? So that's equal to 16. Most elements in the periodic table need 8 electrons to satisfy the octet. That's why it's called an octet. There are a few exceptions. Hydrogen only needs 2. So when you're filling in the needed for hydrogen, as we'll see down here, you just put 2 instead of 8. But normally it's going to be 8 until I get to just a few exceptions. Alrighty. So then to figure out the number of shared, it's just needed, which is 16, minus available, which is 12, and that equals 4 shared electrons. If each bond is equal to 2 shared electrons, and I can even go one step further and say the number of bonds I predict in this molecule is going to be the total shared divided by 2, because there's 2 in each bond. So I'm predicting 2 bonds. All right, so you do all that work ahead, so you have an idea of how many electrons you have available to work with and how many bonds you predict you're going to have in your molecule. All right, then you go back, and according to the rules, and you can refer to the rules, it says draw a skeletal structure. The skeletal structure means you just have to write down all of the atoms that are in your molecule, and then you have to connect them at least by 1 shared pair of electrons, and we'll just use a bond, a little dash, to indicate that shared pair of electrons. So right here, remember, what do you think? When you see this, you think a pair of electrons. So just by putting this thing together, I've just used 12 of my available electrons, okay? So now, once I've used 12 of my available electrons, I'm down to 10. And according to the rules, it says, okay, once you've just stuck the thing together with the minimum amount of bonds to hold the individual atoms together, then you start putting all of your other available electrons on the atoms to satisfy the octet for the atoms. So I've just used 2, 4, 6, 8 electrons of my 12 available. I've satisfied the octet on that one. I'm going to start placing electrons in pairs on the next one, and I just get 2, 4, 6, 8, 10, 12. I've used up all of my available electrons. And so I don't have any more electrons to place, and I have not satisfied the octet on this one because there's only 2, 4, 6. But what I do know is that I should have 2 bonds in this molecule, and I only have 2 atoms. And so to account for the fact that this only has 6 around it, and this has 8, and I only have 1, I should have 2 bonds, is you can move a non-bonding pair of electrons to form what's called a multiple bond. So in covalent compounds, you can have single bonds, which is 1 shared pair of electrons, or, and I'm going to redraw it up here, you can have what we call double bonds, which is 2 shared pairs of electrons. Okay? And so for oxygen then, the one pair that I had originally placed here, I misplaced. I should have placed it here, and I figured that out when I looked at my available and my number of bonds. And it's a rule that's available to you in order to satisfy an octet, just move a pair of non-bonding and make them bonding. And so now I've got what's called a double bond. That's 2 shared pairs of electrons residing between these 2 oxygen atoms. And then I've got a pair of electrons here and a pair here. So I have 2 non-bonding on this one. I have a pair here and a pair here, 2 non-bonding on that one. And so now I can double check and make sure I've satisfied my octet by looking at the sphere around this oxygen atom. I have 2, 4, 6, 8 electrons. Look at the sphere around this oxygen. I have 2, 4, 6, 8 electrons. So I've satisfied the octet, and I have satisfied what I predicted is the number of bonds, which is 2 single bonds. We just call it a double bond. But you count your bonds individually. There's 1, 2. So that's a double bond. So that's 2. This indicates 2 single bonds, which is the same as a double bond. All right. And so anyway, the proper Lewis structure then is this. And sometimes people put the non-bonding pairs of electrons on, and sometimes they don't. So this, you would assume then that you've got these other electrons here. So either with or without the extra electrons. Normally when you're drawing Lewis structures and you're being tested on drawing Lewis structures, the teacher wants you to show all of the bonds. But you'll see in the book a lot of times that it's just drawn like that. That's just because everybody knows that there's 2 non-bonding pairs on each oxygen. I should say everybody who knows anything about chemistry knows that, and now you do too.